Hey everyone, welcome to part 1 of chapter 4 of calculus and vectors. In this video, we'll be talking about curve sketching. We will cover the first 3 sections of the chapter. The first section is increasing, decreasing functions. Then we have critical points, local maxima and local minima, and finally vertical, horizontal, oblique asymptotes. So let's begin. Let's go through increasing and decreasing functions. A function f is increasing on an interval if any value within the interval the function is increasing. So basically what it means is that if we have an interval of 0 to 10, any x value within 0 to 10 the function is increasing. This is also same for the opposite. If a function is decreasing on an interval, any x value within the interval the function is decreasing. In order to determine whether a function is increasing or decreasing is by finding the f prime x. If the f prime x is positive, then the function is increasing, whereas if the f prime x is negative, the function is decreasing. Another way to tell whether a function is increasing or decreasing is by looking at the slope of the tangent. If the slope of the tangent is positive, then the function is increasing, whereas if the slope of the tangent is 0, the function is neither increasing nor is it decreasing. We can say that the function is flat. And lastly, if the slope of the tangent is negative, we can say that the function is decreasing. This is a great example of how we can use tangent to determine whether a function is increasing or it's decreasing. And if we look over here, this tangent has a negative slope. Therefore, the function is decreasing. And over here, the tangent is also negative. Therefore, the function is also decreasing. However, over here, the tangent is 0. So, at this point, the function is neither increasing nor it's decreasing. The function is flat. If you look over here, the tangent is positive, so the function is increasing. And lastly, at this tangent, the slope is also positive, so the function is also increasing. With this information, we can write the intervals of increasing and the interval of decreasing. Over here, the interval of decreasing is negative infinity to 0, and the interval of increasing is 0 to infinity. Now let's look at example 2. Find the intervals of increase and decrease for the function f of x equals 2x cubed plus 3x squared minus 36x minus 4. In order to find whether a function is increasing and decreasing, we need to find the f prime x. We can find the f prime x by deriving the function. So in this case, the f prime x is equal to 6x squared plus 6x minus 36. Next, we make f prime x equal to 0, because when f prime x is equal to 0, the function is neither increasing or decreasing. The function is flat. So if we make f prime x equal to 0, we can write it 0 equals 6x squared plus 6x minus 36. Now we can solve for x. So 0 equals x minus 2, x plus 3. Therefore, x is equal to 2 and x is equal to negative 3. Now that we know when the function is flat, we can now determine the interval of increase and the interval of decrease. In order to find the interval of increase and decrease, we look at the intervals before and after the x values. So the intervals should be negative infinity to negative 3, negative 3 to 2, and 2 to infinity. Now we can use test values to determine whether the function is increasing or decreasing. As I said before, if f prime x is positive, then the function is increasing, whereas if f prime x is negative, then the function is decreasing. So for the first interval, we can say that x is equals to negative 4. And when we substitute x equals negative 4, we get f prime negative 4 is a positive number. Therefore, the function is increasing. For the next interval, we can substitute 0. So f prime 0 is negative, therefore the function is decreasing. For the intervals 2 to infinity, we can substitute 3. When we substitute x equals 3, f prime 3 is a positive number. Therefore, the function is increasing. In this case, we can say the function is increasing from negative infinity to negative 3, union 2 to infinity, and decreasing at the interval of negative 3 to 2. Now, let's look at example 3. Sketch f of x when f prime x is given. As was stated before, if f prime x is positive, then the function is increasing. So, in this case, any interval above the x-axis, the function is increasing. Whereas, if f prime x is negative, therefore any intervals below the x-axis is decreasing. Therefore, we can write the intervals of increase and decrease for the function. So, the interval of increase, negative infinity to negative 2 and 1 to infinity. This is because at these intervals, the function is above the x-axis. And the interval of decrease is negative 2 to 1. This is because f prime x is below the x-axis. Now that we know the interval of increase and decrease, we have to find the interval where the function is flat. In this case, the function is flat when f prime x is equal to 0. So, when f prime x is equal to 0, x is equal to negative 2 and x is equal to 1. Therefore, at x equals negative 2 and x equals 1, the function is flat. With this information, we can sketch the graph. First, let's draw an axis, the x-axis, and this is the y-axis. The easiest way to draw this graph is by first plotting the point where the function is flat. So, the function is flat at negative 2 and at 1. Now we can plot the graph. From negative infinity to negative 2, the function is increasing, and at negative 2 to 1, the function is decreasing, and from 1 to infinity, the function is increasing. So this is how your graph should look. Now let's move on to the second section. Critical points, local maxima, and local minima. So, in order for x equals a to be a critical point, you need to fulfill two criteria. Firstly, f of a must be defined. And secondly, f prime a should either be 0 or undefined. In order to get a better understanding, let's look at an example. So, example 1. Identify the critical points. Firstly, as stated before, f of a must be defined. So, looking at this graph, we can see every x value is defined. So, every x value fulfills the first criteria. Whereas, for the second criteria, f prime a should either be 0 or undefined. As we stated at the section before, at f prime a equals to 0, the function is flat. By looking at the graph, we can see the function is flat at x equals 0.5. So, the critical point will be 0.5, 0.25. Now, let's look at the other possible critical points. As stated before, a point can be a critical point if the f prime a is undefined. When f prime a is undefined, it means that the function is undivisible at a certain point. As we can see in the graph, at x equals 0 and x equals 1, the function is undivisible. This is because it has a sharp corner. So, at x equals 0 and x equals 1, we can say this is a critical point. So, the other two critical points is 0, 0 and 0, 1. In this slide, we will discuss local minima and local maxima. Local minima and local maxima are basically turning points. Before we get into this, let's discuss how we can define a turning point. In order for a point to be classified as a turning point, it needs to fulfill two main criteria. Firstly, f prime a should be equals to 0, means it needs to be flat. Secondly, it must change sign. So let's look at an example. If we have a function behavior something like this, we can see that the function is increasing and then decreasing. Therefore, this is a turning point. However, if a function behavior is something like this. We can see the function is increasing and then flat and then increasing. Therefore, it doesn't change the sign. That means that this point is not a critical point. It's important to keep this in mind when we're looking at local maxima and local minima. So let's now discuss local maxima and local minima. If a function behaves something like this, where the function changes from a negative gradient to a positive gradient, this is a local minima. Whereas if a function changes from a positive gradient to a negative gradient, this is the local maxima. If a function doesn't change the sign, for example, an x cubed graph, is neither a local minima or the local maxima. Now let's look at example 2. For the function fx equals x power 4 minus 8x cubed plus 18x squared, determine whether these values are local maximum or a local minimum or neither. So the first step is to derive the function. So f prime x is equals to 4x cubed minus 24x squared plus 36x. Next, we make f prime x equals to 0. So 0 equals 4x cubed minus 24x squared plus 36x. After this, let's solve for x. So we can write 4x equals x minus 3, x minus 3. Therefore, x is equals to 3 and x is equals to 2. For this example, we need to determine whether a function is increasing or decreasing. Just like the example at the section before, we have to make a t-table and also find whether the function is increasing and then decreasing or decreasing then increasing in order to determine whether it's a local maxima or a local minima. So the first interval is negative infinity to 0, the next is 0 to 3, and then 3 to infinity. In order to determine whether a function is increasing or decreasing, we need to substitute a test value into f prime x. So the first test value we can use is negative 1. When we substitute negative 1 into f prime x, we get a negative number. Therefore, it's decreasing. For the next interval, we can substitute 1. When we substitute 1 into f prime x, we get a positive number. Therefore, it's increasing. And for the last interval, we can substitute 4. When we substitute 4, we also get a positive number. Therefore, the function is increasing. Now that we know the interval of increase and decrease, we can now define x equals 3 or x equals 0 to either be a local maxima, minima, or neither. If we analyze the table, we can see the function is decreasing from negative infinity to 0, and then from 0 to 3, it's increasing. So when the graph changes from negative to positive, there is a local minima. So we can say that x equals 0 is a local minima. So basically, the algorithm to find the local maxima and the local minima of values of the function, first we need to find the critical points of the function. That is to determine where the function f prime x is 0 and where the f prime x is undefined for all the x value in the domain. Next, we use the first derivative to analyze whether the function is increasing or decreasing on each side of the critical number. And lastly, based upon our finding in step 2, we can conclude whether each critical number is a local maxima, local minima, or neither. Lastly, let's look at the last section of this video: vertical, horizontal, and oblique asymptotes. What is an asymptote? An asymptote is a line that a function gets very close to its specific value but never touching it. There are 3 types of asymptotes that a rational function might have. There's vertical asymptote, horizontal asymptote, and oblique asymptote. So let's look at vertical asymptotes. A function f of x has a vertical asymptote at x equals c if one of the following is true. Firstly, f of x is equals p of x over q of x, and p of c does not equal to 0 and Q of C is equals to 0. Another way we can tell whether x equals c is a vertical asymptote is by analyzing the function from the left and the right. If x approaches c from the left and f of x goes to negative infinity or positive infinity, we can say this is an asymptote. This is also same for the right side. If x approaches c from the right and the function goes for negative infinity or positive infinity, it is a vertical asymptote. Let's look at the example. Identify the vertical asymptote. As you can see here, at negative 7, there is an vertical asymptote, because if we analyze the function on the left, we can see that if the function approaches negative infinity from the left, f of x goes up to infinity. Whereas if the function approaches negative 7 from the right, the function goes to negative infinity. We can also identify a second asymptote, which is at negative 3. As we analyze the function, we can see that when x approaches negative 3 from the left, the function goes to infinity. Whereas if the function approaches negative 3 from the right, the function goes to negative infinity. Therefore, in this case, the asymptote is at x equals negative 7 and x equals negative 3. So let's look at example 2. Find all vertical asymptotes for the function f of x equals x over x cubed plus x minus 2. So the first step is to make q of x equals to 0. So q of x is equals to x squared plus x minus 2. So q of x is equals to 0 means 0 equals to x squared plus x minus 2. So now we can solve for x. So 0 equals x negative 1 and x plus 2. Therefore, x is equals to negative 2 and x is equal to 1. That means the vertical asymptote is at x equals negative 2 and x equals 1. It's also important to write the general formula. In order to write the general formula, you can use test values on both sides of the vertical asymptote. So, limit as x approaches negative 2 from the left, f of x equals to negative infinity. Limit of x approaches negative 2 from the right, f of x goes to positive infinity. For the next asymptote, we can write limit of x approaches 1 from the left, f of x goes to negative infinity. And limit of x approaching 1 from right, f of x goes to positive infinity. Now let's talk about horizontal asymptote. The line y equals L is a horizontal asymptote if limit x approaches negative infinity, then f of x is equals to L, or limit approaches positive infinity, then the function approaches L. In order to determine the horizontal asymptote, we need to compare the degree of p of x and the degree of q of x. If the degree of q of x is equals to the degree of p of x, then the horizontal asymptote is equals to the leading coefficient of p of x over the leading coefficient of q of x. Whereas if the degree of q of x is bigger than the degree of p of x, then the horizontal asymptote is at y equals 0, which is the x-axis. Let's look at an example for a better understanding. Identify the horizontal asymptote. So by looking at the graph, we can easily identify the horizontal asymptote. We can see that the horizontal asymptote is at y equals 2. We can determine this by looking at the behavior of the function. As can be observed, when the function goes to negative infinity, it gets infinitely closer to y equals 2. Whereas when the function approaches positive infinity, it gets infinitely closer to y equals 2. Therefore, y equals 2 is a horizontal asymptote. Now, let's look at the next example. Find all horizontal asymptote for the function f of x equals 2x squared over 3 minus x. So for this, first we need to compare the degree of p of x and the degree of q of x. So the degree of p of x is 1 and the degree of q of x is also 1. Therefore, the degree of p of x and the degree of q of x are the same. Next, we use the suitable formula. As what was stated before, when a degree of p of x is equal to the degree of q of x, we use the leading coefficient to determine the horizontal asymptote. Therefore, y is equals to leading coefficient of p of x over the leading coefficient of q of x. So the leading coefficient of p of x is 2 and the leading coefficient of q of x is negative 1. Therefore, the horizontal asymptote is at y equals negative 2. Now let's write it in the general formula. So the limit as x approaches negative infinity, f of x equals to 2 from below. You can determine whether the function approaches from below or above by using test values. For example, we can substitute 100. When we substitute 100, if it's lesser than 2, then it's from below. Whereas if it's bigger than 2, then it's from above. In this case, as limit x approaches negative infinity, f of x equals 2 from below. And when limit x approaches positive infinity, f of x approaches 2 from above. Now, let's look at oblique asymptote. Oblique asymptote is very similar to horizontal asymptote. In order to determine the oblique asymptote, we need to also compare the degree of p of x and the q of x. The oblique asymptote only occurs when the degree of the numerator, which is the p of x, is greater than the degree of the denominator, which is the q of x. So let's look at example 5. Identify the oblique asymptote. Of course, by looking at the graph, you cannot determine the equation of the oblique asymptote. However, we can analyze the behavior. As we can see, as the function approaches infinity, it gets infinitely closer to the oblique asymptote. This is an important thing to keep in mind. Now, let's look at our last example. Example 6. Find oblique asymptote for the function f of x equals x squared plus 12x over x plus 4. As we can see, the degree of the numerator is bigger than the degree of the denominator. Therefore, there is an oblique asymptote. In order to find the oblique asymptote, we need to do long division. X plus 4 and x squared plus 12x plus 0 inside. And now we can do long division and solve this problem. So first we can write x squared plus 4x, and we can write plus 8 over here, and we get 8x plus 0, and we write negative 8x plus 32, and we get a remainder of negative 32. So our equation of the oblique asymptote is x plus 8. Now let's write the general formula. Limit as x approaches negative infinity, f of x is equals to x plus 8 from above. In order to tell whether the function is approaching from above or from below is by using test values. You can use test values and substitute it into the oblique asymptote and also the function and compare those values. If the oblique asymptote is bigger, then the function is approaching from below. Whereas if the oblique asymptote is smaller, then the function is approaching from above. So in this case, limit x approaches negative infinity, f of x equals x plus 8 from above, and limit as x approaches positive infinity, f of x equals x plus 8 from below.